It's Doug Littrell again. This is July 8th, 2017. Sitting on my couch this time in my living room where I have a little too much art on my walls, you might say. I live in a small house alone in Kansas City. Older house, smaller house. Does have a two-car garage though that I like. But, and I like art. I like to do art, but the art I have in my house is all stuff I found when I bought this house about, I don't know, 15 years ago or so. Anyway, I found my explanation for why the objects with the pith ball type experiments, the plastic, the rubber, the wood, styrofoam, etc., why they only attract and then the loading in the wand from the rubbing dissipates. It reverts back to what I would say are the radio shells regain their more rightful particles, and the electric photons are lost because they're attracted to other things. There are other disturbances going on, and so this gives the more rightful particle at that distance from a nucleus more of a opportunity to return to its rightful. It wants to return there, but anyway, this is how it dissipates, what I think is going on. But as far as compared to like a styrofoam bead with a conductor on its surface, like the aluminum that I've made several of those beads with aluminum covering the styrofoam. I've already shown that there's an attraction at first when you rub the wand and hold it next to the bead. There's an attraction at first. Then what's apparently loading from the wand into the conductor, the aluminum foil, that goes on for a couple of minutes or so, and then we're on the very side where it's attracted and it's apparently loading up. It's better if you allow them to touch for that to occur. Then it will jump away and then make the thread angled. You can see that it's repelling. Okay, the difference between these insulators, like wood, like plastic, like rubber, styrofoam, the reason I found my explanation for that. And leading to that, something else is coming into focus with regard to noble gases. I've been thinking about this with noble gases for a long time, but sometimes things just set up so that it's the right time to go ahead and work on that aspect. It's really coming into focus now. I want to explain that. But I'm going to go ahead and tell you what's going on. Now, I wrote this last night. I'm going to read from it, but a few pages. But that's how I figured it out. But I'll go ahead and tell you what's going on with the plastic balls, the wood balls, or pieces of wood, or rubber balls, when you hold the wand that you rub next to them. The good electric conductors like aluminum, okay, they're going to have unfilled radio shells on the outermost. Their outermost shells are going to be unfilled shells. The filled capacity would be they'd be completely spherical, enveloping the nucleus at that distance from a nucleus, and they're going to be in the 30 to 40% range, I think. I thought they were going to be in the 10 to 20% range, the best conductors, but I'm thinking 30 to 40, but that's not for sure yet. But an insulator would have to be, it would either have to be below 10%. It would not be a noble. Well, I'm jumping into my noble gas explanation. It would not be a noble gas. Okay, I'll go ahead and say that. The noble gas is going to be a repeating pattern in the periodic table with elements, that it has the fewest number of nucleons that can have a completed outer shell that's filled. That's why it behaves that way. See, a nucleus, I'll go ahead and just explain it. The nucleus is very attractive, and that's why molecules compounds form, is because it's the nucleus that's able to reach over and connect with another atom, and their radio shells come together, and then there's repel, and they can't come any closer, but they attach, and they'll attach in different patterns. This is the way molecules form. Okay, but there needs to be some leftover attraction over and above what it can hold with its radio part. Now, it's going to hold some radio particles in that outer shell, but if there aren't very many of them, the nucleus is somewhat satisfied. But still, on the other side, where there are not any of that shell, there's not any in that part of the shell. Now, the distance to the nucleus is closer. And so that's where you would have the likelihood of it attracting another entire atom and making a connection. With a noble gas, you have, this repeats as a pattern in the periodic table. It's easy to see. There are basically three, well, if you count deuterium and tritium, there are basically three kinds of nuclei, and then there's helium, a noble gas. And I'm going to kind of jump around with this, because I don't know how to neatly keep everything organized and separated with explaining this. Okay, there's three elements. Well, you wouldn't necessarily call deuterium and tritium an element, but there are three kinds of nuclei, and then there's helium. In my system, I've already assigned 80, and then moved it up to 88 radio particles that would be attracted to a nucleus per its number of its protons. And there would be 110, start out with 100 and then 110, because it needed adjustment when I got to sulfur for things to work out. And so 110 per neutron. Well, now I'm seeing, with this realization about, which I've kind of always known was going to come about, but it wasn't the appropriate time for me to make the step of saying it yet. But it is now. The noble gases are when you have a nucleus of a certain number of nucleons, and it just so happens that its outer shell, okay, all the shells in the elements just prior to that one, smaller in size, they have that shell too, but it's unfilled. And now you have, suddenly you have an element where its outer shell is completely filled. And so and for a filled shell like that, it has it's going, by that shell being filled, it's going to keep away other atoms. That's why it's a noble gas. It's the fewest number of nucleons with the greatest number of protection by radio shells, and complete protection, because that outer shell will be completely filled. And so that's why it doesn't attach to other noble gas atoms of its same type, or others that are also noble gases. Doesn't make diatomic gas molecules, and it doesn't attach in compounds. Now, I think there's one, it might be helium, that in rare instances it does attach, but generally they all remain individuals, and that's why they're called noble gases. So what you have in the periodic table, you have three. Now, I've already done this with assigning 88 radioparticles per nucleus, whatever its number of protons are, and 110 per whatever its number of neutrons are. But what's going to happen now is because this noble gas, because that all the shells leading up to each noble gas have unfilled shells, the farther down you go in the list, the more scant the shell is. You know, you're going to have 10%, then 20%, or you're going to have 12.5%, you're going to have 25%, and then you're going to have, 37.5%, then the next, something like that. But now they're not going to be the same because some of those, they don't always keep the same proportions of protons to neutrons. So it's still going to vary because of that. But they have unfilled shells, and now this nucleus is large enough, it has enough nucleons so that it's able to hold a completed outer radial shell. Now there's three types of nuclei leading up, well actually there's four if you count helium-3, and we'll count that, but anyway, helium-3 is like tritium, only one. In helium and tritium, there are 2 neutrons, and then in helium-3 there are 2 protons and 1 neutron. So there are 3 in each one. But anyway, as far as they're similar in their radio shells, very similar. So we'll just count it as 3 types. You've got protium has a single, proton. Deuterium has a proton and a neutron that are attached. Tritium and helium-3 have, 3 nucleons that are attached. So you have 3 types, and then there would be these first shells. In my system, it's an R3, and then you have an R7, or let's see, pardon me, or an R15. That's the second shell, and helium would have, it would be the first, the R15 shell is filled. You actually have 2 leading up to 2 types of radio shells leading up to helium-4. And then it's completely filled with R15, I think it is. And then you'd have 7 elements leading up to the next noble gas. You'd have lithium, then beryllium, then boron, then carbon, then that's 5. Let's see. Let's do that over. Lithium, beryllium, boron, carbon. Yeah, no. Now we have nitrogen, oxygen, fluorine. Okay, the next is neon. So then you have 7, then you have the 8th is neon, the next noble gas. And so what's going on with this is all of those have an R, I think it's the next shell out is an R4 in my system. So all those have progressively greater filled R4 shells. And then neon has a completely filled R4 shell. And then you have 7 more elements after neon. You have sodium, you have magnesium, you have aluminum, you have silicon, you have sulfur, you have chlorine. Let's see, what am I forgetting here? I was leaving out phosphorus. Anyway, you've got sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, there's 7 again, then argon, the next noble gas. So what you're going to have with this is you're going to have neon had a completely filled, if I got my shells, radio shells right, the right types and the right distance away, making shells from a nucleus, that is. Neon would make, would have a filled R4 shell. And then you begin to add, I believe it's an it might be an R7 shell, I'd have to check. But then you start, let's just say that you start adding the R7 partially filled shells. You get maybe in sodium, it's got, 15% filled shell, I don't know. And it is a conductor, by the way, sodium. Then you have magnesium, and it would have more of that R7 shell. And then you've got aluminum, which is a great conductor. And I believe it's it's why I'm leaning right now to the 30 to 40% filled shell, because when you get to that point, you should be in the 30 to 40% range, and it's a good conductor. Then at silicon, it's a semiconductor, and it would be in the 50 to 60% range maybe. And then after silicon, of that type of radio particle, you have phosphorus, and then you have of course sulfur. Then you have chlorine, which is a gas, and then but of course it attaches in a lot of compounds and makes a lot of solid material. It's key in a lot of solid materials as well, but it's a gas when it's I believe it's a diatomic, makes a diatomic gas molecule. Yeah. Usually when it's on its own, I'd have to double check that. But after chlorine, then you have argon, and then argon would have. See, all these details have to be sorted out because their properties and what they do will have a bearing on how this is done, how this is all sorted out. But I believe I've got something to organize it with, as far as a good interpretive model. When you get to argon, you're going to have a filled R7 shell. Now let me check that and see if it's R7, because this model needs to be refined. I've got it started, and been working on it, but it's just like the electric layer. I've dropped that. That doesn't make any sense. It made sense because electric photons can beat all of the radio particles to any spot, and that there'd be some of them next to the nucleus, but there's reasons to why that doesn't need to be a part of the model now that I'm starting to realize. It's superfluous. So where your electric transmission is happening, and I think this is known by those who have worked on the standard model, it's happening in the outermost shell. That's where this takes place. That's the only thing that really makes sense. Of course, this stuff feeds in. You've got covalence evolved, like I've been talking about. But let me check my shells as they stand at this time to see the order, because I don't look at that stuff, very often really. As far as my radio shells are concerned, I was right about that. You got the R3, then you have the R15, then you have the R4, then you have the R7, then you have the R5, and then you have the R6. I think the R5 is, like I said, it's the dark blue with 4 yellow photons attached. And then when you get to an R6, there's somehow room to attach another photon, and then it pushes the repel up to a higher level than the R5. But anyway, another thing you want to keep in mind with this is, as far as, let's say I start putting together a new periodic table where there is no negative charge, and everything is the number of nucleons that have been found using the system we have, the standard model right now, but you assign what the proportions of the protons and neutrons are according to a certain number of neutrons needing to be kept apart, kept quiet by wedging protons in between them, and they would do that automatically. So that's how you would configure the nuclei. They wouldn't be just a glob that is sitting there sort of vibrating and in fluid. They would be actually wedged into a certain configuration, and that's the way this model would work, because what you see in tritium is that the neutrons are clapping, and so and that makes radioactivity, and so this would be a pattern that is carried forward throughout all of the elements. But anyway, when you get up into these larger nuclei, now you're getting, these shells are getting larger and larger and larger, and voluminous, and it's going to take a lot of radio particles to fill those in a spherical manner. But apparently there are enough of them to do the job, and they're just out there in unbelievable numbers in the environment, ready to do that. But now, we first of all had 3 types of nuclei. Then we had helium. Then we had 7 more unfilled shells. Then we had neon. Then we have 7 more unfilled but progressively more filled shells. 7 again, and then we have argon. And then now when you go to the next step, when you're approaching, what is it, krypton, you have 17 instead of 7. Twice you have 7 in between the noble gases. Now you have 17 from argon, between argon and krypton. And then you have 17 again between krypton and xenon. And so, but look at these, the size of the nucleus is getting much larger, of the nuclei. They're getting much progressively larger, and it's going to take more and more of these radio particles to fill those shells and make them spherical. And so, and when you're adding nucleons, and that's what, a few nucleons from one element to the next, and that's what determines how many of these radio particles are out there. See, the percent of the nucleus, when you have a larger nucleus and you add a proton or 2, or you add a neutron, maybe, and a couple of protons, now it's a much less percent. It's a much less percent of the nucleus every time one is added. That's why the number jumps from 7 between them twice, and now it's 17 between the noble gases twice. Anyway, I'm going to be working on this. I feel, I've spent a number of years kind of working up toward this, thinking about the noble gases, and I feel very confident that this is the real reason why that my system is what is actually occurring in nature. I just need to it needs to be perfected. It needs to be refined. When you're doing something like this, you try things, and we're not divine. We don't have divine wisdom and knowledge. We have to just work things out, make some mistakes, realize we made a mistake, get rid of that, improve it. You know, that's the way reality works when you're dealing with a human trying to find out what's really going on with anything. So, yeah, I'll be working on it. Let's see now the explanation for why the conductor the insulators are attracted only. Okay, now they either had to be just have a little tiny bit of a shell at, let's say, something like right after a noble gas, let's say, in the succession, or they would have to be a nearly filled shell, say 90% filled. And I've come up with the idea that it's 90% is what's causing the wand to be attracted to the plastic, rubber, and wood balls and styrofoam, and there's never repel. That you never build up this loading of electric photons that have replaced radio particles, and now suddenly there's more repel, you know, from the wand that has a lot of those, and now the foil that has a lot of those, and then they jump apart. Okay, there's always, as far as I can tell, there's always attraction, and then it dissipates with the plastic and rubber and wood balls and such, the insulators. So what's going on, I really believe, and this opened up last night while I was thinking about the noble gases and the periodic table, and you know, making a new periodic table, but without negative charge. But what's going on, what I realized looks like is going on, and this is the way it is when you're doing naturalistic explanations. It usually you'll find out you make mistakes, and then you'll usually come up with one thing, and there really isn't any other way to explain it. It almost has to be that. It's the only thing that works. That's what I've been finding out with a lot of these explanations, is that you come up with stuff, you try stuff, they see that it's not right, and then you end up with one that it almost has to be that because there's no other way to explain it. Now, I think that's probably what's going to happen with us. I'm not sure yet, but I think that the insulators have 90% filled shells as a rule, or something like that. They might have an 80% filled shell, and this all may depend on the shell type as well. But let's just say it's a 90% filled shell. Now there's no covalence. It's going to behave like a filled shell somewhat, but there's going to be a few holes, and but it can't circulate. It can't circulate. It's more like an individualized shells over these atoms, and they're next to one another, but they're not filled. But when you bring in, say, something that's being loaded from like a copper wire, or if you know the rubbed wand, let's say you bring in something that's loaded up with electric photons next to it, and it disturbs the outermost shell, several of those, because you know the ball has got lots of atoms on it, actually molecules. They're not pure elements, but anyway, they have let's just say let's take an element that is a insulator. Sulfur apparently doesn't transfer electricity, so sulfur would be like an insulator. There are other elements that are so restrictive to conducting electric current that you could call them an insulator. There are elements. So let's just say there's an element that we have made a ball of, and it's all got all the same atoms, and its shells are not filled, but have a lot of, close to, not that far from being filled. And so you bring the wand that you've rubbed that has all this extra loading of electric photons in it now, and the repel of it disturbs the outer shell and outer shells of all these on the surface of this ball that's, and let's say a ball made of sulfur. And so now I'd have to get a sulfur and see if it behaves the same way as these plastic rubber balls, but let's just entertain the idea here that when you bring it into sulfur, now the sulfur being like an insulator, those shells are going to be disturbed enough to take on some of the electric photons. And when the electric photons are moving into it, there's attraction. There's your attraction right there. That's the attraction. They're moving into all of those outer shells that are not filled, and they can't circulate. Okay. They can't circulate the material, those electric photons throughout it because they're more individualized. But now, the ones that are further in the interior, they feed around to those, and not being a covalent shell that can just move quickly, they're gradually they feed some into the next shell, and then to the next. But it's very slow. It's very slow, and they keep feeding a few more and more. The repel of those coming in makes a disturbance, gives them more opportunity, but it's very, very slow. And they keep feeding more and more into the material. But then the wand is having its radio shells return because some of those are being attracted off. Some of those electric photons are being attracted off to do other things. And then it gives the opportunity for the radio shell to go back the way it was. And then the attraction ends. That's what I think is happening with these insulators. I think they're like something in the range of a 90% filled shell, and they can't circulate, and then it's the traction continues because they're gradually feeding more of these nearly filled shells further and further into the material, and it keeps going, and then it's over because it keeps feeding it, so there's an attraction the whole time, but everything returns to its normal proportions, the radio particles going back, and then it's over.